Hey, Professor.
Good evening.
How's it going? Could I just ask you one question about the project before we
Sure.
start? So we're allowed to, because you said we don't have to turn in our test benches. That means we're allowed to share them with each other, right?
Test benches, yeah, you can always share with each other. I hope you will be referring that into your report, reflecting that.
Of course, yeah. All right, thank you.
All right, 7:30, let's get started. Tonight, what was the topic? Oh, we are starting a new module, memory hierarchies and cache memories and virtual memories and related to that. But anyway, let me hear any questions if you have at this point, either on these or any other topic. Well, let me check if there is any question on the discussion. Nope, there are no questions so far.
I have a question. Oh, go ahead.
I was just gonna ask if you could possibly do an example of calculating the hit rate of a system.
Hit rate? Yeah, sure, we can do that. Or we can reuse. Okay, is there a hit rate discussion right there? Oh, you mean how the hit rate is calculated?
Yeah, that's what I meant.
Oh, okay. So those are maybe next day I will pick up one practical problem, which is kind of tell you how the hit rate is measured, but in general, it is a statistical analysis and also like after the implementation, like there are benchmark program which exercise that and stress test the cache memories, and there they come up with this hit rate and miss rate, all this number on average. So this is a statistical quantity. But nonetheless, I will discuss that in next class. I have one example, I think, to discuss with respect to the cache memory part 2. That problem, and in that problem, we'll pick up the hit rate and miss rate on that.
So like if we were to have a problem like this on like a quiz or something, we'd just be calculating like the total time using hit rate?
Yes, in most of the cases, you will be given with the hit or miss rate, because that's the almost like you can treat it as an intrinsic property of the cache itself. So yeah, so that quantity has to be given to you.
Alrighty, thank you.
So when we're talking about the hit rate and the miss rate, that's it was kind of framed in the idea that there's a one higher and one lower cache memory. What happens if there's like in the previous slides when there was like 3 or 4 levels?
So
is there like a hit rate and miss rate for every level?
Yes, there is a hit rate and miss rate at each level. So as I said, hit rate, miss rate is basically associated with that cache. So L1 cache will have one miss rate versus L2 has another and L3 has another. So yeah. And the just on to add on top of that, the general observation and general requirement is that as you go up in the hierarchy from L1 to L2 to L3 and L4 and so forth, your hit rate must increase. It's not the other way, because as you go up in the hierarchy, your miss penalty become higher. So you want to avoid that. So it's a general thumb rule that we want to increase the hit rate as we go up.
Sorry, Professor, can you repeat what you said? As you go up the hierarchy, the what becomes more expensive?
A miss penalty.
Thank you.
When you say up the hierarchy, do you mean from like a larger memory to a smaller memory, or the opposite?
Other way.
Oh, okay.
So,
Oh, okay, got it.
so it is like you can take the processor as a level 0, lowest level. Okay. On top of that, there is L1, that is first level hierarchy. And then on top of that, there is second level. And there is third level. So as we go up, your size become bigger, right? And interaction block change also become bigger as we go up. So that's why the miss penalty actually also goes up as we go up in the hierarchy. Any other question?
Professor, so about project 2, could you explain like what were the requirements for the reset test?
Hey, can you volume up a little bit? I cannot hear you actually. Kevin, right? Maybe you want to speak like towards your microphone.
Can you hear me now?
Yes, this is much better.
Okay, so about the project 2, so about so what were the requirements for the reset test? So like I talked with a lot of my classmates and a lot of them like also failed the reset test. So I want to know what the requirements are so that like if we need it for project 3, then we can like
So reset is remember the reset is, let's say you are running a computer, right? And at any point of time you can hit a power off or restart button while everything is running. So that means when it comes back after that, it should start normally. So basically this is kind of like a program is running and in between you send a hit like reset. And after that, if you restart the program, your program should like generate the right result. So you see the point here, like you're running a program, in between you hit that reset signal, and after that you load that same program or another program, doesn't matter. But the next program should generate the correct result as if it is starting from power.
Oh, so you're saying like if we like start up some program and then reset, and then after the reset, like the same program runs entirely again, or another program runs entirely again, then
Right.
then it would have the correct result.
Exactly. So what does it mean in terms of implementation, or at least describing the behavior, is that if you hit a reset button, you need to reset your program counter, reset your stack pointer, or whatever register internally. You have to reset it back to the power up state.
Oh, so you're saying like when you get like a reset signal to the control unit, the control unit will like turn everything will like the proc state will become like will be reset, like the proc
Right.
state component will be reset, and in addition to that, like whatever like program counter registers you have inside of your control unit, you also change it to the startup values.
Exactly. Your
Okay,
state become very, so next clock it will start again from the instruction phase. Doesn't matter it was it in the mem phase, exe phase, doesn't matter. You hit the reset button, state goes back to the instruction phase to start with, and then internal registers and all this part also, addition to that, also resetted to the power of values.
Okay. So like all of the values, including like the stack pointer and all
Exactly.
that, so reset. Okay. All right. Thank
Yeah.
you.
Your register file, for example, register file has a reset, right? You took care of that, I believe, in the register test bench and all this stuff. In the reset state, it basically wipe out the content, put everything 0. Same with the memory. It wipes out the content, put everything 0. So same with the control unit. You need to reset into the power up state.
Okay, got it. Also, what happens? So for the last project, when the control unit when it reaches an instruction that is like all zeros because you've already finished the instruction because you only loaded a certain part of memory. What are you supposed to do after that?
So
Like
I
after
think
the program
0, 0 is a NOP, right? Nor is there a function? Because in this project, I don't care, but that's a valid question and good question. What we do, right? What the processor does. So remember, in terms of processor never hits such scenario. It always runs something. What it runs? It runs the operating system code. And operating system code is such a way it always like, do something, either wait on the user or do some management, these or that. So processor does not actually hit such a condition that it is in such a program counter which doesn't have instruction. Right? Unlike our case is very bare minimum, basic, no operating system, nothing else is running. So that's why you get you hit such a problem. And definitely, I think I'm not sure if I have given you the NOP or NOP condition. All 0 means no operation, just don't do anything. But it's kind of executing that NOP throughout that. Okay, but in real life, operating system will do something, will this and that.
Okay. Thank you.
Hey, Professor, would you be able to go over one of the questions from the last quiz?
Sure.
It was the one on the number, how many cycles will the processor take to complete a shift left 10?
So basically, it was, I think that problem was given that it uses that ALU discussed in the lecture 11, which is a sequential ALU. In that, we are using the sequential shifter, which uses the shift registers. And if you look at that very specific instruction, which is something like SLL, some register, and shift amount is 10. So that means your shifter inside the ALU will complete that operation in 10 clock signal, right? 10 clock cycle. Then what it becomes in terms of the whole instruction execution. Your instruction is executed in 5 cycles, but EXE stage has to have a handling of that point where EXE state won't assume that ALU will be done in 1 clock cycle. It will wait for the down signal from the ALU that many cycles. So that means we are adding 10 extra cycle for this instruction on top of the regular 5 cycle of the execution. So your answer is 15, 10 plus 5, 15.
Great. Yeah, I missed the fact that it was a sequential ALU. Thanks, Professor.
Okay. All right. What else? Okay, let's try to do one problem regarding hard disk. Okay, let me share the screen. Okay, so here's a problem. Okay, So in this problem, it is saying that we are comparing between two computing systems. One using the traditional hard disk, and other is using the solid state disk. Okay, so let's see. Okay, so you see we are comparing between traditional disk system versus a solid state disk system. Here a couple of information are given to you that transfer data to the main memory at minimum unit. So unit of transfer from the rotational traditional disk is 2 kilobyte of block of data. That means it has to adjust its read-write head per 2 kilobyte of data access, and its average access time is 1 millisecond. Means to place that read and write head on the proper position is 1 millisecond per block it will occur, and the transfer rate is 100 Mbps. So here you notice that your Mbps, B is in small, lowercase, right? This means it is bits per second. It's not byte per second, it's bits per second. Okay, Mbps, megabits. So that is given for the traditional disk, and for the solid state disk, it says that it's transfer the data with a 1 kilobyte of block of data. So other was 2 kilobyte block of data transferred to the main memory. This one is 1 kilobyte block of data, and it has an access time of 50 microseconds per block of data transfer, and refresh time of 250 microseconds. So after each block of transfer, it needs 250 microseconds to refresh itself and all these electronic circuitry, etc., etc. It takes that much of time. Now, question is, we are loading this machine and booting up a Linux system, let's say with initial size of 2 megabytes. So 2 megabyte must be transferred from the hard disk to the main memory in order to complete the boot process of that operating system. Question is, which system will boot faster and how much? We need to have the performance ratio. So I'll let you take 5 minutes to think about this problem. Then I'll open up the breakout room for your teams to discuss and come up with a solution for this problem. All right, so 5 minutes starts now. And you can, of course, ask me any question if you have on top of this, on this problem. Okay, I'm opening up the breakout rooms now for 10 minutes. Okay, please discuss it with your peers and come up with a solution of this problem. Okay, let's wait for a couple of more seconds for everybody to come back and join into this main session. Let's see. Yeah, I think we have everybody. So who has the answer? What is the final outcome of this problem? Anyone want to share? Yes, no?
Would the would the formulas that we used be from, it would be from today's notes, right?
Uh, it Yeah, it is. It is. It is more like a concept than the formula itself.
Okay. Because I'm not sure, because I don't know if I don't know if I did it right, so I don't want to say anything. But I kind of followed like for the random access one, I did the 1 divided by the memory cycle time.
Okay.
Was that what that one was supposed to be using? Oh, wait.
I don't know. What's your final answer? Like how fast or slower is that system is?
I don't know if I got that far. I think all I got so far was the transfer rate.
Okay.
For the first one, I got, or not for the first one, the second block of data, I got 0.0033 microseconds, but I'm not sure if that's right.
Okay. All right. Anyone else? Okay. Why don't I try to solve it and see what's going on there? So this has like two systems. So we'll calculate with respect to two different system. One is the traditional disk, right? One is the traditional. Okay, what is it? What is it? Yeah. So one is the traditional disk, right? So let's talk about the traditional disk. So given from this information that 2 kilobyte block of data, first thing we compute is number of blocks, which is how much data we need to move. We need to move 2 megabyte. So obviously number of blocks equal to 2 megabyte by 2 kilobyte, which is like we can actually nullify these units. This goes out, then it is megabyte by kilobyte, which is like 2 to the power 20 by 2 to the power 10. Mega by kilo, that unit, which is 2 to the power 10, which is 1024. So number of blocks we need to transfer from the disk as in traditional disk system is 1024 blocks. Now, as the given problem, its access time is 1 millisecond. That means we can roughly say, or at least we can claim that it will need to position its read-write head, right? This part, right? 1024 time. That means I have total time, total access time equals 1024 multiplied by 1 millisecond, and which is basically 1.024 second in terms of second unit. Now let us consider how much time it involves to transfer the real data from the disk to the memory. To do that, we need to do how much time it needs for the first block for each block. Okay, for each block. So it's how do we calculate that? it will be like each block transfer time is a 2 kilobyte of data, and its rate, transfer rate, is 100 MB, megabits per second, right? So it is basically boils down to, let's say we change this unit to byte, to bit, this byte unit to bit, which means this is effectively 8 kilobit by 100 megabit second. This unit will nullify each other. 1 kilo is 2 to the power 10. 100 M is 2 to the power 20, which is about 0.16 multiplied by 10 to the, no, not 10, 2 to the power minus 10 second in terms of, okay? So since we have total 1024 blocks, so total transfer time is 1024 multiplied by 0.16 multiplied by 2 to the power minus 10, which is nothing but 2 to the power 10, 0.6 multiplied by 2 to the power minus 10, which is 0.16 second. And total time, total boot time, that means in this case would be 1.024 plus 0.16 seconds. So I'm basically picking up this value, which gives me 1.184 second. 1.184 second. Okay, now the next part. Next part is the solid state disk. We'll do the similar approach. For this guy, your number of block, this is a solid state. Number of block equals here.
On your, what's the word, stream, you haven't switched over to the next slide.
Oh, sorry. Yeah, thank you. Yeah, so this is 1 kilobyte of block for 2 MB. So 1 KB by 2 MB. Okay, 1 KB by, oh, sorry, other way. 2 MB by 1 KB, which is basically 2 to the power 10. And that is basically 2048. So 2048 blocks need to be transferred. And we can take more or less the average transfer time. We can take it as summation of this plus this. Okay, per block it will take to transfer 50 microsecond, and after each transfer it will take like 250 microsecond for refresh time. It actually takes 2047 refresh time, but we can just add one more. That won't basically give much difference in the performance ratio because it's too tiny number. So we can just approximate to that the transfer time per block 50 plus 250 microsecond, which is 300 microsecond. That means boot time equals 2048 multiplied by 300 microsecond, which if you multiply it 3, 4, 4, 1, 6 microsecond, which okay, okay, wait a minute. 2048 multiplied by 300 microsecond, which is this many microseconds, right? Yeah, 3, 1, 6 microsecond, which is 1, 2, 3, 4, 5, 6, 0.6144 second. Then performance between is the execution time of the rotational disk by solid state disk SSD, which is rotational was 1.184 by 0.6144, which is approximately 1.93. So it is kind of an like almost 2x faster on the boot time for the solid state disk. Question? There is some comment on the chat. Let me review it. Zfan has the same result, 1.983. That's good. Alexander Olsky has a question. Can you use blocks that are larger than 2 KB since 2 KB only minimum unit of size? Alexander, what do you mean by this statement? Like, can you use larger than 2 KB?
Well, in the instructions, it said, at least for the hard disk example, that 2 kilobytes was the minimum unit, 2 kilobytes of block. So I was wondering if that meant you could use blocks that were 3 kilobytes or 4 kilobytes and reduce the access times.
Okay. Let's not assume that. I see what you're saying at a minimum. What it basically try to say, I believe, in this problem is that you cannot go below that, and also it is always in the hardware circuitry, this number is fixed. Like you're not able to configure it. Like once it is done at the circuit level, 2 kilobyte transfer, it is a 2 kilobyte transfer. You cannot do anything more or less than that.
I see. So when we see this in a problem, we can just assume it's a fixed size of block.
Right.
All right, thank you.
Okay. All right, let's take 5-minute break then. Then we'll be back with more topics. And if you have any other questions, we can discuss them. Okay, let's come back, resume our session. So you see from this problem, the what we did is we definitely see the solid state disk has a higher performance, but at least on the booting time perspective, and you will see like I think many of you have experienced that when you used to have the solid state, sorry, uh, traditional rotational disk laptop versus the when you switched over to the solid state disk. If you have, then the experience would be boot time is super fast. It just almost instantaneously it boots, or at least with compared to the traditional disk, right? So that is one part of the benefit of having a solid state disk drive in a system. Uh, Apart from that, when we study about the virtual memory system, we'll see that part of the disk is also used as a memory in a system. And in that sense, if you use a faster disk system, which is solid state disk drive, your performance, overall average performance of the system will be boosted up, because your virtual memory function would be much faster. Like all these, like it picks up part from the memory, copies back to the disk system as a part of the virtual machine, and so on and so forth. We call it a page saving, page restoring, and all this stuff. We'll come across that in the last lecture. But it basically solid state disk help there to boost your performance, and you'll see lot better performance with a machine with a solid state disk. So I'd suggest if you are thinking to switch over to a new laptop or anything like that, consider solid state disk if you have not already. Question? All right, now pop quiz time. I have pop quiz 8. Please go to your canvas and let me distribute this poll. If you are ready to enter the passcode, please hit yes on that poll. It's pop quiz 8. So far 51 out of 67 voted yes. We're ready 54. So it will be again like 10-minute pop quiz, 10 questions, just like other ones.
Hey, Professor?
Yeah.
Is this like the pop quiz that we missed, or is it on today's module?
It's basically the previous.
Okay, cool. Thank you.
$64 out of 67. Let me wait a couple of more seconds for 2 more. 65 of 67. Okay, let me share the password then. Pause this password. Okay, here it go. 10 minutes starts now. Oops, where is that? Maybe 1 more minute for everybody, I believe. Then we'll see. Okay, I think quiz time is over. Let me see if I can see the stat on this quiz. To share. Yep, here is your stat for today's pop quiz. 55% average, not a great score. 90% high, that's okay. I think we could do better in both areas. And I have opened up this quiz for you guys. You can see your grade. And if you have any question, let me know, okay? Or any doubt or anything, just send me an email about that. All right, how is the project 3 coming up?
Not great.
Not great? What happens, friend?
Oh, it's just a lot. Speaking of which, we were collectively wondering how you would feel about a possible extension.
Not really, not possible.
Okay. just figured I'd ask just in case.
Yeah. And if you look at the rubrics, like it's not that if you cannot finish it, the processor, it is not end of the day. I hope you have seen the rubric. Let me see what is there in the rubrics. I believe I had a breakdown there somewhat. Project 3. Yes, so if you see, apart from the report rubrics, let me share my screen again. Okay, so apart from the report rubrics, you see that there are testing and points for each of the, almost each of the lower level module. Like ALU as a whole has some points. The shift 32-bit barrel shifter has some points. Full adder itself has some testing point. Half adder itself has some testing point. And all this lower level like NOR 32, inverter 32, all these things has testing points. So that means if you are partial in your project implementation and if your lower level component works fine and you confident they're working okay, you still get a good marks in this project, even if you don't pass the system level testing as a whole, which includes the controller and the data path and all this stuff. If you can finish up the before that level, don't finish data path, don't finish control unit, you can still get a good marks. And your report needs to be reflect truly like whatever part you did, it needs to include that and also mention that okay, for this reason you could not finish up like the complete thing. That's okay too. Like, so don't get panic if you cannot finish. Historically, like many students could not finish this project, especially the reason is already given by Yavav. Mr. Fire, a lot of coding. Yes, it can be a lot of coding. You can do a little bit like trick on that part. Like, for example, you can use that genvar approach to minimize the code, but your debug level would be higher. You can do scripting, which spits out the Verilog code. I hope you have realized by now that it is kind of a very systematic code and it has a pattern in each line, right? Each line of code has some patterns and you can actually make it a program to generate that pattern. So that can help you in this project as well. But if you write it purely by hand at the very basic minimum get level, yes, it will be a lot of coding because it's a 32-bit system we are talking of. Question?
Can I ask a question about the signed multiplication circuit?
Yeah, sure.
So we have to implement a 64-bit like complement module that turns whatever 64-bit signal into his 2's complement version, and that's used for the product of the unsigned multiplier. So from the unsigned multiplier, we get two outputs, the high and the low. So do we use that 64-bit like complement module and like take those two signals, concatenate them and put them into the 64-bit?
Yes,
okay.
You can route it through some buffer, 64 buffer, and make it part of one bus, 64-bit bus. You can do that.
Also, in that 64-bit like complement module, you need to have a 64-bit NOT. So can we just use the two 32-bit NOTs and like put half of the signals into one the other?
Sure.
And the same thing for the multiply. So we need a multiplexer, a 64-bit multiplexer, so we can just take two 32-bit multiplexers, and then at the end we can take the 64, the outputs of those two, and like assign that to the final.
Yeah. So that is the whole that is the whole point here. You need to reuse modules as much as possible, like, and build up the complex module based on the simpler module. Don't try to code it all the way till like basic logic level, like AND, NAND. That will be too much to code, like a 64-bit multiplexer. So you use higher level module, as you said, like 32-bit multiplexer, and somehow logically combine them to build up a like 64-bit multiplexer, for example.
Okay. And one more question about the adder. So we had to make a 32-bit adder and a 64-bit adder. So are those two basically the same thing, except for the fact that the 64-bit version has 64 full adders instead of 32?
Yeah.
Okay. And it's not like the 32-bit adder, like we like instantiate two of them inside the 64. We can just like copy.
No. And you can actually reuse the 32-bit adder as well. Like what needs to be done, you use LSB part one adder and MSB part the other 32-bit one adder. But from the LSB side, the final carry out becomes a carry in for the other part.
Yeah, so you can do it either way, right?
Yeah,
Okay.
Either way.
All right, thank you.
Any other question from anyone? All right, good night then. Let's close tonight's discussion and see you all on Wednesday.
Thanks, Professor. See you Wednesday.